All right, welcome Physics C students to the first video from Unit 2. We've gone over some of this in class, but just in case someone was absent, or maybe I'll use this in another year, you'll go over this first page again. Unit 2 here is worth 25 to 20% of the AP test. This is Isaac Newton. He was born in 1642, died in 1727. A famous quote of his says, "If I have seen further, it is by standing on the shoulders of giants." And he was specifically referencing Kepler, Copernicus, and Galileo, because without their research and data, he would not have been able to see as far as he did, or to come up with the achievements and realizations that he was able to. These are the equations on the equation sheet that you'll get for the AP test. Here are Newton's three laws in his original words, which were in Latin. The first law is that every body perseveres in its state of rest or uniform motion unless it is compelled to change that state by forces impressed thereon. And in modern language, this would mean any change in speed or direction is caused by an unbalanced force. Of course, a change in speed or direction is an acceleration. So this just says accelerations are caused by unbalanced forces. Newton's second law, which we know is sigma F equals ma, in Newton's words was the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. We can see some hints of vectors when we talk about the direction of the straight line there. And Newton's third law says, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. My translation of that would be forces always occur between two objects. Each object experiences a force of equal size, but in an opposite direction than the other object. We're going to go on to the next page and do the next couple pages. Please make sure you copy down everything. We're looking at situations without friction and without any drag right now to keep things simple. We will work up to friction and drag in the coming videos. The first situation we're looking at here is static equilibrium. Static equilibrium is when we are at rest and forces are balanced. There's also such a thing as dynamic equilibrium. That's when you are moving and forces are balanced. Static, at rest, dynamic, moving, equilibrium means balanced forces. So in this first example, let's apply Newton's second law to the traffic light that's hanging here. We'll need to define a few things first, like a coordinate system. I'm going to use a standard coordinate system where we have plus x to the right and plus y going up. I can draw another parallel line right here and use alternate interior angles. This angle is going to be theta 2, and this angle would be theta 1. Those angles are not congruent, so maybe I'll put a second slash in there to make the geometry teachers happy. T3, the tension in the lower chord, we can get that by saying that T3 up and the force of gravity down on the light are equal. So we get T3 equals mg for the traffic light. And that was based off of sigma F equals 0. Now, if we move up to the other junction here, where all the chords come together, and we drew a free body diagram there, we'd have tension 3 going down, tension 2 going up and to the right, tension 1 is going up and to the left. Remember, for a good free body diagram, your arrows need to start on the dot and point away. You need to label the arrows with the names of the forces, not formulas. So don't put mg for force of gravity. Use Fg or W for weight. And don't break your forces into components. Just show the overall force and the direction. If you break it into components on an AP test, you could lose points. Also, if you have to draw two forces that are parallel, they should be drawn as two separate parallel arrows, not overlapping arrows starting on the dot. So we've got our free body diagram. Let's look at the forces in the X direction first. In the X direction, we know the sum of the forces is equal to 0. That means that tension 2 in the X direction, which is to the right, positive, minus tension 1 in the X direction, which is to the left and negative, those are going to equal 0. So we get T2X equals T1X. And the X components of these, we can find using the angle here. The X component is adjacent to the angle, so we would use cosine. This is going to be, this is going to be T2 cosine theta 2 equals T1 cosine theta 1. Then in the Y direction, we will do something very similar. The sum of the forces in the Y direction equals 0. We have three forces in the Y direction. We have T1 in the Y direction, which is up, T2 in the Y direction, which is up, and T3, which was down, so it's going to be negative. This means T1, and in the Y direction, we're going to use sine of theta. So T1 sine theta 1 plus T2 sine theta 2 equals T3. We'll just move T3 over to the right. And if we wanted to, we could replace T3 with mg, which would be the force of gravity on the traffic light. So there's an example of breaking components, breaking forces down into components for a situation of static equilibrium. These next three examples are to indicate that the normal force is not always equal to the force of gravity. That's a common mistake that some students make. Only in the middle case here do we have the force of gravity actually equal to the force from the supporting surface, the normal force. So if we were to draw a free body diagram, which we already kind of have here, right? Normal force up, gravity down. Another name for gravity is weight. So this is also Fg. Fg and capital W, same thing. We know that sigma F in the Y direction equals 0, and that means that the normal force is equal to the force of gravity. Take a look at this example on the left. Here we have three forces. There's a ground supporting things here. They're not just floating. So we're going to have the force of gravity on the box. We're going to have the normal force on the box. If I really wanted to be accurate, I would make that normal force smaller than the force of gravity. All right, so I took two boxes here. This is less than 2. They're not looking for that level of accuracy on an AP test. Many times you don't know the magnitude of the force when you're drawing it. You don't need to be overly concerned with that. I'm doing it here just because we have a force of tension coming up this way, and that force of tension is going to be at some angle here. We'll call that theta, the most common symbol for an angle. And if we apply Newton's laws here, we know sigma F y equals 0. That means that the normal force, which is up, plus the force of tension in the y direction, which is going to be T sine theta, minus the force of gravity equals 0. And that means that the normal force is equal to the force of gravity minus T sine theta. So tension pulling up supports some of the weight, and it reduces the amount of the weight that the normal force needs to support. You can imagine an object on a scale. If you put something on a scale and you pull up on it without lifting it off the scale will read less, right? And over on the right side, this is going to show that the force of gravity, or the force normal, can sometimes be greater than the force of gravity. We again start with sigma Fy equals 0. We don't know exactly what's happening in the x direction. Well, in fact, in this case, it looks like we'd have an unbalanced force in the x direction and the object would experience acceleration to the right. In this case, we have three forces in the y direction. We got our normal force up, and it alone has to equal both gravity down and the amount that this force, the applied force, is pointing downwards, right? So the up force has to equal both of the down force, so this needs to be bigger than just gravity. This would be like pushing an object down onto a scale. When you push down on the object, the scale is going to read a greater weight than the object actually has. So we have the normal force up minus mg, which is down. It's important to note that you shouldn't do this on a free body diagram. At least I think it's the best practice not to. Use names for the forces like Fg or W. And then we also have the applied force, which is F applied. And we're going to use sine of theta for that one as well. If we solve this out for the normal force, you'll find that it's equal to mg plus Fa sine theta. So the normal force in this case is increased above what it would normally be. Next page. We've got a block on a ramp. There's no friction and no drag here. And when we're sliding up and down a ramp, we're going to use a tilted coordinate system, so the motion is one-dimensional. It doesn't really matter whether you say up the ramp or down the ramp is positive. So you could have a coordinate system like this, where y direction's there, and this would be the positive x direction. Or you could have a system like this, where plus x is up the ramp, and then you have plus y. Either of those will work. Okay. Either of those work. We should remind ourselves here that mu equals 0, there's no friction. And with using the tilted coordinate system here, the object only moves in the x direction. That's the benefit of using a tilted system. If we used a standard system where the x coordinate was parallel to the bottom and the y coordinate was vertical, then as the object moves up or down the ramp, it's really moving in two dimensions. It would be moving in both the x and the y direction. It just makes using Newton's laws harder. If we make a free body diagram here, what's a free body diagram going to look like? Well, we're going to have the force of gravity straight down, and then the normal force comes off at an angle. And if I break this into components, I'll still have Fg going down. The normal force will be like this. And then to break this into components, I make this into a little right triangle. There's the right angle. This would be Fgy, which kind of points down. And then this would be Fgx, pointing down the ramp. So Fgy pulls us into the ramp, and FGX is pulling us down the ramp. One of them is perpendicular, one of them is parallel. So the X component is the one that's parallel to the ramp, and the Y component pulls us into the ramp. Now we'll need to use trig functions for breaking this down into FGX and FGY. So we should think about what makes sense, sine or cosine, for the force of gravity parallel to the ramp or perpendicular to the ramp. What's going to make sense here? I missed an L. Parallel. So at 0 degrees, if the ramp was at 0 degrees, how much of gravity would pull you down the ramp? None of gravity pulls you down the ramp when the ramp is at 0 degrees, because down the ramp is then horizontal. Gravity doesn't pull horizontal. So we know to use sine for down the ramp. Down the ramp is the X direction. So for the X direction, which is parallel to the ramp, I'm going to have sigma F in the X direction equals mass times the acceleration in the X direction. And this is Fg in the X direction equals ma. And then I'm going to use Fg sine theta equals ma. And of course, that's mg sine theta, right? Force of gravity is mg. So mg sine theta, that's our force down the ramp. And for perpendicular to the ramp in the y direction, that's the amount of gravity that pulls us into the ramp. We're going to have sigma Fy equals 0. And what we get there is Fn, which is in the positive y direction, minus Fgy equals 0. And since we used cosine in the x direction, we're going to use cosine in the y direction. Sine for the x direction, cosine for the y direction. Does that make sense that cosine is used for the y direction? Yes, because at 0 degrees again, how much of gravity pulls you straight into the ground at 0 degrees? All of gravity does. And cosine of 0 would be 1. I really like this technique about thinking about angles that you know, like 0 degrees, and using those to choose trig functions rather than just memorizing or turning this into a geometry problem. You can make similar triangles, and you will figure out eventually that this angle here is theta. But I much prefer thinking about what trig function works rather than just memorizing or doing a geometry problem, because the technique of thinking about what you know and relating it, understanding it, will help you in many other situations down the road in this course and others. Next, we're looking at an Atwood machine. Atwood machine is named after George Atwood. He lived from 1745 to 1807. He was an English mathematician, and he invented the Atwood machine for illustrating the effects of Newton's laws in a slower fashion than just like dropping things under the force of gravity. Now, for an Atwood machine, we want to use a curved coordinate system. And the benefit of using a curved coordinate system is that it turns this into a one-dimensional problem where everything is moving in the same direction. So if we assume that M2 is larger than M1, which is an assumption, we're not told that, but it looks bigger, so we'll go with it for now, then my coordinate system here would be like this. I'd want plus to be down here. I'd want minus to be down on that side. That means that as object 2 falls down, it's moving in the positive direction. Right? As this one comes down, it's moving in the positive direction. And as this one goes up, it's moving in the positive direction. That means both of their accelerations are positive. Both of their velocities are positive. Both of their displacements are positive. It makes everything positive, and it just makes it easier to deal with. A quick free body diagram here. We'd have the force of gravity on number 2. This would be tension. Here we'd have the same thing, tension, and we'd have the force of gravity on number 1. Notice that although gravity points down for both of these, on the right side, down is positive and tension would be negative. On the left side, tension is positive and gravity, according to our coordinate system, gravity going down is the one that's going to be negative. Now, the other way that you can think about this coordinate system is if you were to draw this as a 1D drawing, where we would have to unfold this from the pulley. Now, I wouldn't make these 1D drawings on a AP test, but this shows you kind of what we have. If I was to make this a one-dimensional drawing, okay, this would be object number 1. We'd have our string. It would be connected to object number 2, and we would have the force of gravity on number 2 pulling to the right. I would have the force of gravity on number 1 pulling to the left, and in the middle here we'd have tension. Tension would pull to the right on number 1 and to the left on number 2. You can kind of see how this all is like a one-dimensional problem where to the right is positive and to the left is negative. That's essentially what we have done over here on the left with this tilted coordinate system. So, a standard way of applying Newton's laws here is to say that I'm going to deal with M2 first. For M2, we have sigma F2 equals M2 times the acceleration. The sum of the forces on M2, we had mg down on the right, which was positive, minus tension, and that should be m2g. Right, we got to be careful with our masses. m2g equals m2 times the acceleration. For m1, we'll come up with a similar system. Sigma f1 equals m1. I don't need to put A1 because A1 and A2 are the same. They're both positive, and they're both the same magnitude of acceleration. So tension was positive on number 1, and tension is the same for both objects here. So T minus M1G equals M1A. Now, if I combine these equations, I just kind of write them. I'll take number 1 first. T minus M1G equals M1A. Then I have M2G minus tension equals M2A. And I add these together, and I'm using the addition method here. You'll notice that when I add these, the two tensions cancel each other out. And I'll be left with M2G minus M1A. 1g equals m1a plus m2a. And we could easily solve that for the acceleration, right? If I wanted to solve for acceleration, I would factor out this a. I'd be left with m1 plus m2 times quantity m1 plus m2 times a. And then I would divide that over to the other side. Now, there's another approach that you can take to these kind of problems. The other approach is a little more straightforward. It is a system m1 and m2 together. And for a system approach, you only use external forces, which means no tension, because tension now is a force between M1 and M2. Maybe I should say M1, M2, and string. So tension is now a force between M1 and M2. And since it's not external to the system, it won't affect the acceleration of the system. So with only external forces, I need to say the sum of the forces on the system equals the mass of the system times the acceleration. It is okay to use a system approach on an AP test as long as you make it clear that you're using a system approach by using subscripts like this, right? You got to say system, you got to say system. I have taken points off because people didn't make it clear whether they were using a system approach. The other time that I've maybe had to take points off is if the instructions on the FRQ specifically say apply Newton's laws to each object. If you are instructed to apply them to each object individually, you may not use a system approach. So the sum of the forces on the system, we had the force of gravity on number 2, which was down on the right and positive, minus the force of gravity on number 1, which was down on the left, negative, equals the mass of the system, m1 plus m2, times the acceleration. So what do we get? We get m2g minus m1g equals m1 plus m2 times the acceleration. And if you see, this is exactly the same thing that we came up with, right? If you distribute that acceleration in, we get this. Which method is faster and easier? Pretty clearly the system approach, but you got to know how to do it both ways. Because I have seen FRQs where they tell you, apply it to each object, create a system of equations. So you got to know how to do it both ways. All right, we got one more example to do, and that's going to wrap it up. No friction, no drag. This is a modified Atwood machine. We have two masses, but one of them is on a ramp now. For the mass that's on the ramp, I'm going to use a coordinate system that's parallel to the ramp. I'm going to say this is down. This down the ramp is plus x. Perpendicular to the ramp plus y. And then for this one here, we're still thinking about a curved system, right? This is plus, means this is going to be minus. So for this object here, we're really doing like plus is up, minus is down. This will again guarantee that they have the same acceleration, the same velocity, and the same displacement. All of those are vector quantities, so they're going in the same direction, so we make that direction positive for each of them. If we draw some free body diagrams here, M1, that's the object on the ramp. What do we have? We're going to have tension going up parallel to the ramp. We're going to have a normal force on number 1. And then we're going to have gravity coming straight down, Fg1. For M2, the hanging mass, simpler, we have Fg2, and we have tension going up. So we can now apply Newton's laws for each of these objects here. Here we're going to get sigma F2 equals M2A. Tension was in the positive direction. Gravity was in the negative direction. And we'll get T minus M2G equals M2A. For M1 in the X direction, I'm going to have sigma F1X equals M1A. That is the force of gravity in the X direction on number 1, minus tension, which was pulling it up the ramp, which was negative, equals M1A. Force of gravity was M1G sine theta minus T equals M1A. In the Y direction for number 1, we're going to have sigma F1Y equals 0 because the mass is not jumping off the ramp. It's not crashing through the ramp, so we know the forces are balanced in the Y direction. That is the normal force minus the force of gravity in the Y direction equals 0. And we'll get Fn minus M1G cosine theta equals 0. Okay, maybe I should have spread this out a little more. Sorry about that. I had extra room. I didn't realize it. You don't have to go back and reorganize your work or anything. Just make sure it's on there somewhere. And so all of this was for number 1, and that's for number 2. And this is a system of equations, right? We got 3 equations. You could combine these using substitution or addition method as needed to solve for whatever variable you need. And that's going to wrap up this video. We'll be back soon with another video on friction. Until then, take care.